Alrighty. We are starting on procedures. So last night I watched the lecture on procedures. Fortunately, I'm ripping out pages of this book. Alright. Yeah, last night I watched a lecture on procedures. He kind of covered the main highlights of the chapter. But it wasn't like super in depth. So I imagine we're going to go a lot deeper on this one. So let's go to chapter 3 and problems. So we're going to have lots of problems on this one. All right, procedures. Procedures are a key abstraction in software. Is my mic picking up? Yeah. Test. I don't want to clip too much. Okay, so procedures are key abstraction in software. They provide a way to package code. They implement some functionality with a designated set of arguments and an optional return value. This function can then be invoked from different points in the program. Well-designed software uses procedures as an abstraction mechanism, hiding the detailed implementation of some action while providing a clear and concise interface definition for what values will be computed and what effects the procedure will have on the program state. Procedures come in many guises. In different programming languages, functions, methods, subroutines, handlers, and so on. But they all share a general set of features. There are many different attributes that must be handled when providing machine-level support for procedures. For discussion purposes, suppose procedure P calls procedure Q, and then Q executes and returns back to P. These actions involve one or more of the following mechanisms. Passing control. The program counter must be set to the starting address of the code for Q upon entry and then set to the instruction, and P following the call to Q upon return. Passing data. P must be able to provide one or more parameters to Q, and Q must be able to return a value back to P. Allocating and deallocating memory. Q may need to allocate space for local variables when it begins and then free that storage before it returns. This is stack allocation, not heap allocation. x86-64 implementation of procedures involves a combination of special instructions and a set of conventions on how to use the machine resources, such as the registers and the program memory. Great effort has been made to minimize the overhead involved in invoking a procedure. As a consequence, it follows what can be seen as a minimalist strategy implementing only. Sorry, let me reread that. As a consequence, it follows what can be seen as a minimalist strategy implementing only as much of the above set of mechanisms as is required for each particular procedure. In our presentation, we build up the different mechanisms step by step, first describing control, then data passing, and finally memory management. The runtime stack. A key feature of the procedure calling mechanism of C and in most other languages is that it can make use of the last in first out memory management discipline provided by a stack data structure. Using our example of procedure P calling procedure Q, we can see that while Q is executing P along with any of procedures in the chain of calls up to P is temporarily suspended while Q is running. Only it will need the ability to allocate new storage for its local variables or to set up a call to another procedure. On the other hand, when Q returns, any local storage it has allocated can be freed. Therefore, a program can manage the storage required by its procedures using a stack, where the stack and the program registers store the information required for passing control and data, and for allocating memory. As P calls Q, control and data information are added to the end of the stack. This information gets deallocated when P returns. As described in section 344, the x86-64 stack grows toward lower addresses, and the stack pointer RSP points at the top element of the stack. Data can be stored on and retrieved from the stack using push-q and pop-q instructions. Space for data with no specified initial value can be allocated on the stack by simply decrementing the stack pointer by an appropriate amount. Similarly, space can be deallocated by incrementing the stack pointer. When x86 procedure requires storage beyond what it can hold in registers, it allocates space on the stack. This region is referred to as the procedures. Boom, boom, boom. Stack frame. And we get our nice little diagram. Okay. So this is a general stack frame structure. Stack can't be used for passing arguments, for storing return information, for saving registers, and for local storage. Portions may be omitted when not needed. So stack pointer is at the top of the stack, but at the lowest address. Stack bottom is at the highest address. You get your earlier frames. And then the frame for calling P has a number of arguments on the stack that weren't passed as registers. And then the return address. And then the frame for execute has some saved registers, some local variables, and argument build area. So it builds up arguments there. Okay. I wonder if that would be part of the next frame. Okay. Figure 325 shows the overall structure for the runtime stack, including its partitioning into stack frames. In its most general form, the frame for the current executing procedure is always at the top of the stack, and procedure P calls procedure Q. Excuse me. It will push the return address onto the stack, indicating where within P the program should resume execution once Q returns. We consider the return address to be part of P's stack frame since it holds state relevant to P. Code for Q allocates the space required for its stack frame by extending the current stack boundary. Within that space, it can save the values of registers, allocate space for local variables, and set up arguments for the procedures it calls. The stack frames for most procedures are a fixed size, allocated at the beginning of the procedure. Some procedures, however, require variable size frames, like variable length arrays. This issue is discussed in section 310.5. Procedure P can pass up to 6 integral values, i.e. pointers and integers, on the stack. Can it pass a lot more than that? Doesn't it pass the 6 integer values as registers? But if Q requires more arguments, these can be stored by P within its stack frame pointer to the call. In the interest of space and time efficiency, x86-64 procedures allocate only the portions of stack frames they require. For example, many procedures have 6 or fewer arguments, and so all the parameters can be passed in registers. Thus, parts of the stack frame diagram to figure 325 may be omitted. Indeed, many functions do not even require a stack frame. This occurs when all the local variables can be held in registers, and the function does not call any other function, sometimes referred to as a leaf procedure, in reference to the tree structure procedure calls. For example, none of the functions we have examined thus far require stack frames. Control transfer. Passing control from function P to function Q involves simply setting the program counter PC to the start address of the code Q. However, when it later comes time for Q to return, the processor must have some record of the code location where it should resume the execution of P. This information is recorded in x86-64 machines by invoking procedure P with the instruction call Q. This instruction pushes an address A onto the stack and sets the PC to the beginning of Q and pushes address A. The push address A is referred to as the return address and is computed as the address of the instruction immediately following the call instruction. The counterpart instruction ret pops an address A off the stack and sets the PC to A. The general forms of the call and ret instruction are described as follows. So you can say call to a label, which the linker will fill in, and then call star operand, which is probably going to be, I guess it could be a memory address or maybe a register, and then ret return from call. These instructions referred to as call Q and ret Q in the disassembly outputs generated by the program objdump. The added suffix Q simply emphasizes that these are on x86-64 versions of the call and return instructions, not IA32. In x86-64 assembly code, both versions can be used interchangeably. The call instruction has a target indicating the address of the instruction where the call procedure starts. Like jumps, a call can be either direct or indirect. In assembly code, the target of a direct call is given by a label, while the target of an indirect call is given by star followed by an operand specifier using one of the formats described in figure 3.3. Boop. Alright, figure 326, illustration of call and ret functions. The call instruction transfers control to the start of a function while the ret instruction returns back to the instruction following the call. Executing call, after ret. So after the call, 4568, because it took presumably 5 bytes to encode this instruction, is pushed onto the stack. Stack pointer now points to that, and the instruction pointer is put to 540, which is somewhere else in memory. And then after the return, we go back to 568. And the stack is popped. Makes sense. Figure 326 illustrates the execution of a call and ret instruction for the mult store and main functions introduced in section 322. Following are excerpts from the disassembled code for the two functions. So beginning of function mult store, return from function mult store, and then call to mult store from main. In this code, we can see that the call instruction with the address 400.563 in main calls function mult store. Let me look at the disassembly here. So mult store immediately pushes RBX onto the stack, probably because it's a caller saved register, and then moves RDX into RBX. I've seen this pattern before. I don't fully understand it. but I've seen that multiple times now. And then return from function mult store ret q, and then call to mult store from main. So it's going to call q to that address, and then we're going to move. There's just some other instruction afterwards, irrelevant. So in this code, we can see that a call to instruction with address 400.563 in main calls function mult store. This status is shown in figure 326a with the indicated values for the stack pointer and the program counter. The effect of the call is to push the return address onto the stack and to jump to the first instruction in the function mult store at address so and so. The execution of the function mult store continues until the ret instruction at return at address so and so. This instruction pops the value so-and-so from the stack and jumps to this address, resuming the execution of main just after the call instruction. As a more detailed example of passing control to and from procedures, figure 327a shows that the disassembled code for two functions, top and leaf, as well as the portion of code in function main where top gets called. Each instruction is identified by labels L1 to L2 in leaf, T1 to T4 in top, and M1 to M4 in main. Part of the figure shows a detailed trace of the code execution in which main calls top, causing top to call leaf. Function leaf returns 97 to top, which returns 194 to main. So let's look at this. So you got disassembled code for demonstrating procedure calls and returns. So we got leaf, top, and main. So main down at the bottom, we just have our call to top and then some other code afterwards. The top goes in here, X is an RDI, so it subtracts 5 from RDI, and then it calls the leaf. It keeps RDI where it's at, so RDI goes into the leaf and is now Y, in which case Y gets added 2 to it. So net has been subtracted 5, added 2, so it's subtracted 3 total. And then we stored an REX that can be returned. So now REX goes back up to line 7, and we add REX with REX, which doubles the result, and we return that. And then we move REX to RDX in the main. So if we look at the execution trace of the example code, so call Q, RDI is 100, call into top, and then there's the entry of top. We call this the subtraction of 5, and then we call leaf, and then we do this LEA thing, which adds 2. So now we got 97, and the RDI value, it's irrelevant, so that's why I do dashes, but it actually is set to something. So return 97 up the stack, resume top, then top, wait a minute, top does the add, which converts in 194, and that's returned up to main. Makes sense? Using the stack to store return addresses makes it possible to return to the right point in the procedures. When, the first 3 columns describe the instruction being executed, including instruction label, address, and instruction type. The next 4 columns show the state of the program before the instruction executed, including contents of register RDX, REX, and RSP, as well as the value at the top of the stack. The contents of this table should be studied carefully as they demonstrate the important role of runtime stack in managing the storage needed to support procedure calls and returns. Instruction L1 of leaf sets REX to 97, the value to return. Instruction L2 then returns. It pops so-and-so from the stack. In setting the PC, it is popped to this pop value. Controls transfer back to instruction T3 of top. The program has successfully completed the call to leaf and returned to top. Instruction T3 sets REX to 194. The value to return from top. Instruction T4 then returns. It pops so-and-so from the stack, thereby setting the PC to instruction M2 of main. The program has successfully completed call to top. And return to main, we see that the stack pointer has also been restored to that value, the value it had before the call to top. Yep. We can see that this simple mechanism of pushing the return address onto the stack makes it possible for the function to later return to the proper point in the main program. The standard call return mechanism of C and of most programming languages conveniently matches the last in, first out memory management discipline provided by a stack. So this is part of the ABI. So every language has like its separate ABI, and some of them aren't like they're not actual interfaces that you can program against, because the language authors want to be able to change the ABI without worrying about breaking people. So they basically say like, we can change this whenever we want. Whereas the C ABI is like fixed in stone. Like I know Go and Rust are two languages that don't have a stable ABI. And Go does things like multiple return values, and I think it does that just by putting them on the stack. I don't think it uses registers for return values. It probably uses registers for arguments. Alright, you got a practice problem here. So it's 332. The disassemble code for two functions first and last is shown below, along with the code for the call to first by function main. Disassembly of last. So first calls last, and last is a leaf, and main calls first. So each of these instructions is given a label similar to those in figure 327A. Starting with the calling of first 10 by main, fill in the following table to trace instruction execution through to the point where the program returns back to main. Oh, it's a big table. Oh, Jesus. Okay, well, I'm going to have to do it my little markdown table generator. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 by 1, 2, 3, 4, 5, 6, 7, 8, 9. 11 rows, 9 columns. We'll do file, new table. 11 rows, 9 columns. Create, and then we'll fill in these. So this is going to be instruction, and then that's going to be 3 state values at beginning. That'll be the rest of them. And then here we got label, PC, instruction, RDI, RSI, RAX, RSP, star RSP. It's probably dereference of RSP, and description. And then we got M1 0x400560 call Q, RDI is 10, doesn't matter, RSP is 0, X, 7, F, FF, E820. So that's 1, 2, 3, 4, 5, 6. Doesn't sound right. 1, 2, 3, 4, 5, 6. Yeah, 6 bytes for pointer? Doesn't make sense. That does not make sense. Yeah, 6 bytes. Oh, that's right, because we only use 48 bits for addresses instead of the full 64, which means that there's 16 bits, which is 2 bytes. So basically, we leave 2 bytes on the ground for future expansion or whatever. Dash, this will just be call first of 10. Alright, and then this would be F1. Probably be faster for me to just click here, fortunately. This would be F2. Actually, you know what? I'll just do generate and copy to clipboard. Paste it in here. Kill that. Make this thing bigger now. Alright. So now I can go in here, do these really fast. F2, F3, F3, L, L1, 2, 3, F4, M2. Okay. And then I'm going to bring this header down there, and then I'll merge these. And we'll space this out a little bit here. Maybe like that. State values. Something like that. Okay. So these labels, we can trim this down because those aren't needed, which means something like that. These can all be 0x. Okay. Oops. All right. Now that we got our table going, let's go back to our... Can you please go back to the previous page, please? Nope, doesn't want to do it. Okay. I think it's because it was too wide. Yeah. Okay. So at M1, our PC is at 400, 560. Bam. And then do a call queue. RDI is 10. RDI is the first register in the calling convention, right? First argument. RDI is indeed the first argument. Then we have RSI. What is RSI again? RSI is the second argument. Stack pointer, derived from stack pointer, okay. Then REX is the return value. So when we complete this, the stack pointer is gonna be +8 basically, because it'll have a pointer stored on it. The pointer is gonna be this address here. So that's gonna be stored on the stack. PC is gonna be now this location. Oops, which is 400,548. And then 400,548 is this instruction here, which is an LEA. RDI is still 10. This is the state at the beginning of the, before the instruction was executed. RSI is still that, RAX still that. Our RSP has been updated by the previous instruction. It updated this. Our dereference to RSP. Okay. That's what value is stored in RSP will be this value here. So that's why they have that, because they want to know what the return values are. I'm going to do a 0x on this. And then we'll need to add 3 spaces. And then this instruction is going to be our LEA, which is adds 1, x plus 1. Which, alright, that completes this row here. If we look at the instruction here, we're taking RDI, which is x, and we're adding 1 and storing it RDI, so that'll be 11. And then we advance our program counter. Oh no, that's a sub. Sorry, this one here. We advance our program counter to be here. That's going to be a sub. Our RSI hasn't changed. Our RAX hasn't changed. Our RSP is the same. Our dereference to RSP will obviously be the same. And then this will be a x minus 1. So again, we're still oh no, we stored this in RSI. This is saying, hey, load effective address. So take RDI. Sorry, I messed this up. Take RDI. I'm not storing it in RDI. So RDI stays at 10. Take RDI, add 1, and store it into RSI. So that's going to be 11 here. Okay. And then the sub will take RDI. So this will be something like, yeah, okay. RDI subtract 1 from itself. So this will now have 9 stored in there. RSI is left unchanged. RAX has not been assigned yet. RSP is still the same. Same thing here. The program counter is now here. So it's 400,550. 400,550. And then this is going to be a call quad word. And this is going to be call last. Okay. 1, 2, 3, 4. Oops. Something's going wrong there. That? Okay. Okay, when we call, we increment our stack pointer. So that's going to be a 3, 4. No, because it's hex. This is going to be 3, 0. And then our dereference of our stack pointer is going to point to the instruction after the call, which is this. Okay. Our registers are going to remain the same. And then our instruction is going to go to this 40540, which is this guy up here. Okay. And then his description is just U. Okay. His instruction is going to be for a mov. Okay. And then his state, executing this instruction, RDI into RAX, is saying, hey, take RDI, put it into RAX for the return. So that's just a straight out move. 9 still exists there. Okay. Our stack pointer will be the same, as well as our dereference to our stack pointer. Okay. And then we advance to this instruction. And that is a imul. And it says U times V here. U times V. Okay. So when we perform the imul, it's between RSI stored in RAX. So it's 9 times 11, which will be 99. Oops. Nine times 11. Right? Because RSI times RAX, RSI times RAX stored in RAX. And then RSI is still 11. RDI is still 9. Our stack pointer is the same. Our dereference to our stack pointer is still the same. Alright, and now we move to the next instruction here. And that's going to be a write queue. And the description is just a return. Oops. Okay. Now the return pops from the stack, so that's going to decrement the stack pointer back to this value. And it's going to jump to this value. And it's going to set, since it's pointed there, this back to there. Okay. RAX stays the same. RSI stays the same. RDI stays the same. Alright, so we go to 400, 555, which is now another return. A rep Z return. That's the padding when I do that. Just extra padding for AMD 64. So that's another return. Okay. And that's of course gonna do the same thing where it pops the stack here back to that value. And there's going to be no value here now, or whatever value was there. We're going to end up jumping to this location here. Sorry, this is another rep Z ret Q. Okay. RDI will be the same. RSI, same. RAX, same. Okay, what's that? 400, 565 is now a move. This is moving RAX into, just call this a move. I don't think it cares what we call it here. Let's say resume. Okay. All right, let me check my results here. Where's my pen? So I'm just going to read them out of the book here. So I'm going to read the PCs: 400, 560, 548, 54C, 550. 540, 543, 547, 555, 565. Call Q, LEA, sub, call Q, move, mov, imol, ret Q, rep Z, ret Q, mov. RDI is 10, 10, 10, and then the rest 9s. This one's dash, dash, and all 11s. RAX is all dashes down to L2, which turns it to a 9, and then 99, 3 99s after that. RSP is E820. E88. Oh, it's decremented. Damn it. My bad. So this becomes 18. Yeah, my bad, my bad. This becomes 10. I don't know why I thought I totally forgot that it's decremented. I was like, yeah, just increment the stack pointer. All right, 820, 818, 818, all the way 3 of those, and then we got 3 810s, and then 818 and 810. Sorry, 820. Go back to this one. That's just a typo there. Cool. RSP, I should have these right though. 565. 3 times, 555, 3 times, and then 565. Okay. So I had the semantics right. I just had the actual numbers for the stack pointer because I didn't really think. For some reason, my brain just like defaulted to incrementing the stack pointer. Even though I absolutely know that you decrement it. Just a brain glitch. Okay. That was a fun little practice problem. Not too difficult, but gives us a little bit more practice. Data transfer. In addition to passing control to a procedure when called, and then back again when the procedure returns, procedure calls may involve passing data as arguments, and returning from a procedure may also involve returning a value. With x86-64, most of these data passing to and from procedures takes place via registers. For example, we have already seen numerous examples of functions where arguments are passed in registers RDI, RSI, and others, and where values are returned in register RAX. Where procedure P calls procedure Q, the code for P must first copy the arguments into the proper register. Similarly, when Q returns back to P, the code for P can access the return value in register RAX. In this section, we explore these conventions in greater detail. With XA664, up to 6 integral, i.e. integer and pointer arguments, can be passed via registers. The registers are used in a specific order, with the name used for a register depending on the size of the data type being passed. These are shown in figure 328. Arguments are allocated to these registers according to their ordering in the argument list. Okay. Oh. Registers are used in a specific order and naming according to argument sizes. But what's interesting about this is that we waste a lot of space if we're passing a bunch of small ints like chars. You're wasting like 3 bytes? No, you're wasting 7 bytes if you pass chars. So yeah, let's reread this. Arguments are allocated to these registers according to their ordering in the argument list. Arguments smaller than 64 bits can be accessed using the appropriate subsection of the 64-bit register. For example, if the first argument is 32 bits, it can be accessed as EDI. When a function has more than 6 integral arguments, the other ones are passed on the stack, assuming the procedure P calls procedure Q with n integral arguments such that n is greater than 6, then the code for P must allocate a stack frame with arguments such that, then the code for P must allocate a stack frame with enough storage for arguments 7 through n, as illustrated in figure 325. Just want to look at that again. It copies argument 1 through 6 into the appropriate registers, and it puts argument 7 through n onto the stack, with argument 7 at the top of the stack. When passing parameters on the stack, all data sizes are rounded up to a multiple of 8. With the arguments in place, the program can then execute a call instruction to transfer control to procedure Q. Procedure Q can access its arguments via registers and possibly from the stack. If Q in turn calls some function that has more than 6 arguments, it can allocate space within its stack frame for these, as illustrated by the area labeled argument build area in figure 325. Okay. As an example of argument passing, consider a C function proc shown in figure 329, which is over here. This function has 8 arguments, including integers with different numbers of bytes, as well as different types of pointers, each of which is 8 bytes. The assembly code generated for proc is shown in figure 329b. The first 6 arguments are passed in registers. The last 2 are passed on the stack, as documented by the diagram of figure 330. This diagram shows the state of the stack during the execution of proc. We can see that the return address was pushed onto the stack as part of the procedure call. The 2 arguments, therefore, are at positions 8 and 16 relative to the stack pointer. Sorry, my mind was wandering there. hasn't even been an hour and I'm already like gassing out here mentally. My mind is distracted by other things. It's hard to focus when you're distracted. All right, let's resume. As an example of argument passing, consider C function proc shown in figure so-and-so. This function has 8 arguments, including integers with different number of bytes, as well as different types of pointers, each of which is 8 bytes. The assembly code generated for proc is shown in figure so-and-so. The first 6 arguments are passed via registers. The last 2 are passed on the stack, as documented by the diagram in figure 330. This diagram shows the state of the stack during the execution of proc. We can see that the return, let's go ahead and look at that. Okay, so we got our C code. We got 1, 2, 3, 4, 5, 6, 7, 8. 8 different arguments. We got a long, int, short char, and we got pointers to those. And then here, we just take the values passed and we add them to the pointer, the location where the pointers are pointing to. So then we get our generated assembly code. So the first thing it takes is RSP. So RSP is a stack pointer. It takes the stack pointer plus 16 and stores that in RAX. Okay, because each one of the stack pointer things is... Okay, because the stack pointer is pointing at the return address when you enter the function. And so if you go up 8 bytes, then you're pointing at the second to last, or sorry, the last argument. And if you go up 16, you're pointing to the second to last. Oh no, that's not the order that they were put in the stack. Interesting. I would have thought A4 would have been RSP plus 16. And then A4P would be RSP plus 8, but I guess that's not the case. Yeah, I wonder why they passed the arguments that way. I guess they are in order now in memory address. Let's ask AI. Say, hey, in AMD 64 CABI, what order are the arguments past 6 placed on the stack? So say 7 through 10. Yeah, it's weird that the higher addresses. I mean, it doesn't necessarily not make sense, but it means that you push them in reverse order onto the stack. But when the callers are referencing them, it kind of makes a little bit of sense to do it that way, because then you're just saying, hey, the first one's at plus 8, second one's at plus 16, so on and so forth. Yeah, right to left. The caller pushes them right to left. The call instruction then pushes the return address, placing it below argument 7, yeah. Why do they get pushed right to left and not left to right? Variadic functions. Interesting. I never actually looked into how variadic arguments are implemented in C. I know how to use them. There's like a bunch of pound defined macro stuff. But I never looked at how that stuff was implemented. Like, how does a function know that it was given a certain amount of arguments? Is there some type of like integer that is passed to it? Maybe that's what it does. Well, I guess I learned something. I should highlight that. Okay, let's go back to the text. As the diagram shows the state of the stack during the execution of proc, we can see that the return address is pushed onto the stack as part of the procedure call. The two arguments therefore are at positions 8 and 16 relative to the stack pointer. Within the code, we can see that different versions of the add instruction are used according to the sizes of the operands. Add Q, add L, add W, and add B for char. Observe that move L instruction, line 6, reads 4 bytes from memory. Following add B instruction only makes use of the low order byte. Alright, practice problem. Wow, this RDI had a lot of stuff, a lot of space here that was unnecessary. Why don't we just blow all that away? I'll do it here first. Go. Alright, so we got 333. A C function proc prob procedure probability has 4 arguments, U, A, V, and B. Each is either a signed number or a pointer to a signed number, where the numbers have different sizes. The following has the function has the following body. It compiles to the following x86 code. Is this going to be like a multi-page thing? Yeah, that's silly. So I have to skip over this diagram, go all the way over here. They should just like, I guess they're trying to minimize the amount of paper. Determine the valid ordering and types of the 4 parameters. There are 2 correct answers. Okay, let's just grab the C code here. Actually, no, I'm not going to do that because it's going to take forever. So it has 4 arguments. We don't know the ordering: U, A, V, and B. And then the first instruction takes A, which is like an integer value, I guess, assigns it into where U is. B goes into V. And then we return the size of A and plus the size of B. So that's the code. So the first thing that happens here is we do a move signed extended long to quad word. So that'll zero out the, or it'll assign extend to the quad word size. Okay. And we're doing that for, I gotta get my register table up here. So we have EDI. EDI, let me put a pen in here so I don't forget where I'm at. EDI is the first argument. So it goes DI, SI, DX, CX. DI, SI, DX, CX. So because we're taking EDI and putting it to RDI, that means that basically we're sign extending it to RDI is the first argument. And then we add RDI to the dereference of RDX. So now we already know that RDI is going to be A. And DX here, we know that's an R. Dereference is what it's getting added to. So U. I mean, it could do these out of order because they don't have dependencies on each other. The compiler can do out of order execution. Doesn't have to do these in order. So that's probably why I said there's 2 answers. All right, and then we add a byte of SIL. The fuck is SIL? Oh, it's SI low order bits. SIL to RCX. SIL is now, so EDI was the register for A. SIL appears to be the register for B. And then RCX is a register for V. So it looks like this is like a 32-bit and this is a single byte. Because SIL is just a single byte. I think that's it. And then we move 6 to EAX. Which would be one, wait a minute, that doesn't make sense. 6 to EAX? SIL is a single byte. EAX is 4 bytes. I think they fucked up here. This book always fucks shit up in these problems. But SIL is a single byte. And EDI is 4 bytes. Now, if this is SI, it would be 2 bytes. So when they say size of A and B is equal to 2, that doesn't make sense to me. It's impossible. Or sorry, size of A plus size of B is equal to 6 does not equate. Determine the value ordering and types of the 4 parameters. So it's going to be ABUV. A is ordering and types of 4 parameters. This would be int. B short. I'm gonna say short because of the 6 here, but technically it's a char. The register used means this is a char, but the book is crazy. And then U and V, we'll just say void star. Or I guess we know that U is being used with A, right? RDX is with RDI, which is EDI. So A and U go together. Yep, A and U go together. So RDX would be a int star, and this will be a short star. AB UV. Let me delete all that. All right, let's check the answers. ABUV on 333. This problem is a bit tricky due to the mixing of different sizes. Let us first describe one answer and then explain the second possibility. If we assume the first addition, line 3, implements U star plus A, while the second implements V plus B, it's supposed to be V star plus equals B. Here we can see that A was passed as the first argument to EDI and converted from 4 bytes to 8 bytes. Before adding it to the 8 bytes, this implies that A must be a type int and U must be a type long star. Oh, because it was extended. That's right. We can also see that the lower order byte argument B is added to the byte pointed to by RCX. This implies that V must be a type char star. Oh. Interesting. Add byte sil into there. We only add the lower order byte. Okay. But the type B is ambiguous. It could be 1, 2, 4, 8 bytes long. This ambiguity is resolved by noting the return value. Yeah. So the book isn't crazy. I take it back. Sometimes it is though. 6, computed as a sum of size A and B. Since we know A is 4 bytes long, we can deduce that B must be 2. The annotated version of this function explains these details. Alternatively, we can see that the same assembly code would be valid if the two sums were computed in assembly code in opposite ordering as they are in the C code. This would result in interchanging arguments A and B and the arguments U and V, yielding the following prototype. BAVU or ABUV, yeah. And then U is a char, V is a char. ABUV, int short, long star, char star, int short, long star. Okay. All right. I kind of messed that one up. I got these two types wrong, but I got the ordering right, and I got the two types here correct. But I didn't deduce the types of the pointers correctly, because I did do a sign extension to the full size, so I should have assumed that it is a long. And then they only copied a single byte, so that should have clued me into it being a char. That was a big confusion I had, was these two. This long star, if I spent more time thinking about it, I think I would have gotten that, as well as this. But yeah, did learn something there. All right, let's move on. Where are we at now? We're at local storage on the stack. So far it's just been using the stack to store the return pointer and any arguments past the 6th argument. But now we're going to use the stack to store whatever we want. Mainly like temporary variables, stack variables, variable length arrays can be stored on the stack. Yeah, I think that's really all that comes to mind. Yeah, all the locals. Oh, when you save registers before you call a function, you could save those on the stack as well. So yeah, a few different things. Most of the procedure examples we have seen so far did not require any local storage beyond what could be held in registers. At times, however, local data must be stored in memory. Common cases of this include these. There are not enough registers to hold all of the local data. The address operator is applied to a local variable, and hence we must be able to generate an address for it. You can't generate an address for a register. Some of the local variables are arrays or structures, and hence must be accessed by array or structure references. We will discuss this possibility when we describe how arrays and structures are allocated. Typically, a procedure allocates space on the stack frame by decrementing the stack pointer. This results in the portion of the stack frame labeled local variables in figure 325. As an example of the handling of the address operator, consider the two functions shown in figure 331. Okay, so let's take a look at those. 331A. So we got swap add and caller. So caller calls swap add. Let's go ahead and look at that first. So let me get my pen here. So we have arg1 and arg2, and then we call swap add with references to arg1 and arg2, computes the sum, might mutate those values, and then we take the difference between arg1 and arg2 and just put that in diff, and then we do a multiplication. The swap add dereferences xp, copies it to x and y locally, and then copies those values into the opposite memory location, and then returns the sum of them. Okay, let's go back to the text. Function swap add swaps the two values designated by pointers xp and yp, and also returns the sum of the two values. The function caller creates pointers to local variables arg1 and arg2 and passes these to swap add. Figure 331b shows how caller uses a stack frame to implement these local variables. The code for caller starts by decrementing the stack pointer by 16. This effectively allocates 16 bytes in the stack, letting s denote the value of the stack pointer. We can see that the code computes arg2 as s plus 8 and arg1 as s, just s. Okay, I thought the return address would be necessary, but I guess it's not calling into anything, so it doesn't have to. No, the locals are after the return. Okay. We can therefore infer that local variables arg1 and arg2 are stored within the stack frame and offsets 0, 8 relative to the stack pointer. When the call to swap add completes, the code for the caller then retrieves the two values from the stack, computes their difference, and multiplies this by the value returned by swap add and register rex. Finally, the function deallocates its stack frame by incrementing the stack pointer by 16. We can see with this example that the runtime stack provides a simple mechanism for allocating local storage when it's required and deallocating it when the function completes. As a more complex example, the function call proc shown in figure 332 illustrates many aspects of the x86-64 stack discipline. Despite the length of this example, it is worth studying carefully. It shows a function that must allocate storage on the stack for local variables. So there's another example on 332. Okay. Despite the length of this example, it's worth studying carefully. It shows a function that must allocate storage on the stack for local variables, as well as pass values in the 8th argument function proc. The function creates a stack frame diagrammed in figure 333. Okay, that's nice. Looking at the assembly code for call proc, we can see that a large portion of the code, lines 2 to 15, involve preparing to call function. Say 3 to 15? Yeah, or lines 2 to 15. Basically the whole top of it is just calling proc. This includes setting up the stack frame for local variables and function parameters, and for loading function arguments into registers. As figure 3.33 shows, local variables 1 through 4 are allocated on the stack and have different sizes expressed by their locations as offsets relative to the stack pointer. They occupy bytes. Pointers to these locations are generated by LEAQ instructions. Arguments 7 with the value 4 and 8 are stored on the stack as offsets 0 and 8 relative to the stack pointer. Okay, we'll look at that in a bit. Let's look at this first one though. So it just does a swap add. We didn't look at the assembly. So example procedure definition and calling code must allocate a stack frame due to the presence of address operators. Well, we're making progress here. One page at a time. Slow progress, but we're making progress. It's been an hour and 20. All right. I don't want to look too far ahead in the book because usually that just like I don't know. Okay, I'll look ahead. So we got local storage and registers, recursive procedures. Oh shit. We're almost done with this. I didn't want to get too excited because I thought I still had a long way to go on this chapter, but this wasn't a very long chapter. It's only a couple pages. 1 page, 2, let's say 3 pages, 4, 5, 6, 7 pages at most. Most of it's code too. Well, that's exciting. So the next section is going to be on array allocation and access. And if I vim up readme, array allocation and access is next. If we look down into the lectures, data and advanced topics are the next two. So we got probably these is data. maybe these two as advanced. I'm not sure. What I want to do though is I want to re-watch the lecture for procedures, even though I'm like almost done with this section, because I watched it last night and I understood most of what he was saying, but not to a level of detail that I wanted, because it was late at night. I was like eating dinner, and yeah, it was, my brain wasn't really receptive. So I think what we'll do here is I'll finish these 7 pages in the problems. So finish this section out. That'll probably put me at like 2 p.m. So I'll take a break there, get a snack, and then I'll start watching the lectures for not only for the data thing, but for also for, I'm going to rewatch the lecture for procedures. And so that'll be like 2 hours or so. And that'll get me ready for the next section of reading. It's nice when the pages between where I'm reading and the answer key are going down in size. Because the answer key is at the end of every chapter. These are big ass chapters. We're in chapter 3, and the chapter 3 ends on page 386. That means like on average each chapter has been like 100 and what, 30 something, 120 something pages. That's pretty crazy. 127 or something like that. 128. What's 128 times 3? Python. Yeah. It's actually more than that. I guess it's appropriate for a computer book to have chapters that are 128 pages each so far, on average. All right, enough messing around here. Let's get into this assembly. So we got this caller. It's calling into swap add. We don't have the implementation of swap add in assembly here. It's fine. But they just wanted to demonstrate the stack discipline here. So the first step is subq16 RSP. And what that's doing is it's decrementing the RSP16 to allow us to store 2 elements on the stack. And these might be for local variables. Yeah, that's what they're for. And then we copy in to there the 2 arguments. So that takes us down to 5. And then we have this load effective address quad word, where you say, hey, get an address to that and store it in RSI. Which makes sense, because RSI is the first argument, I think. No, second argument. And then RSP is already pointing at where this first argument is. So we put that into our DI. And then we call our swap. And that gives us back EAX. And then we move the value that is in arg1 into RDX, and then we subtract off the value that's in arg2. So now RDX has our diff, and then we multiply our diff with our return value, which is called sum in the code. And then we add 16 to the stack pointer to remove the stack space that we're using for our locals. And then we return. Makes sense. Okay, let's move on to the next part here. And read all this code as well. They said it's worth doing. So we have C code for calling function. So it's a just a normal function, has a return value of a long, so 8-byte return value, allocates a bunch of stuff locally on the stack here, and then calls a proc with a bunch of different arguments. So we got x1, x2, x3, and x4. One's a long, one's an int, one's a short, one's a char. I bet you get 8 bytes for all of them. And then you call proc with the value followed by its address. And I know you get 8 bytes for each one of those. You might not use them, but you're going to get 8 bytes regardless, especially for 1, 2, 3, 4, 5, 6. X4 is a char, but I think the stack space is still going to be 8 bytes for that. Okay. Oh, it looks like the stack space is not 8 bytes for the locals. So if we add up these, we got long 8, 9, 10, 11, 12, 13, 14, 15. But if you 8, 16, 32, yeah. Okay, so there is 8 bytes for each. So we got 32 byte stack frame. So that's weird. But we put 1, 2, 3, and 4. Oh, we got a little diagram over here. Let's just use that. So the return address that we're returning from is on the stack. And then x1 is 8. And then x2, 3, and 4 can all be packed into 8. And then we have to pass argument 8 itself. What about argument 7? Oh, argument 7 is at the stack pointer. And then we'll have another return address popped onto the stack. Okay, that makes sense. Kind of feel like you need to do a diagram like that every time you look at the assembly code just to understand what the hell they're doing. So we store everything in there, which is 8 bytes, 4 bytes, 2 bytes, 1 byte, all stored in that range. And then we do this thing where we load effective address quad word of RSP and 17 into RAX. So that is going to be why are we putting this in RAX? That's the return value. So we store x4 as argument 8. And then we just put 4 directly into argument 7. And then the rest we just put into registers. Oh, and because we need to have x4 be... Isn't x4 already in memory? Okay, so we store its address in RAX. And then how do we pass that address? Because I don't see RAX. Oh, we just do it on immediately the next instruction. We take RAX and put it into the stack. Okay, that makes sense. We do that because we can't read and write from memory in a single instruction. Okay. Then we call our procedure and then retrieve changes to memory. So why do we, these are just things that we're just reading from our stack, our temporary space. We're doing our addition, we do our subtraction, and then we do a multiply, and then we add 32 to our stack space, to a stack pointer to deallocate the frame, and then we return, which pops the address off the stack. And now the stack is left with just its arguments that it previously passed to us. Okay. Let's go back over here. I'm going to reread the text on this just to make sure that I'm following everything. This is code setting up the stack for local variables as function parameters and for loading function arguments into registers. As figure 333 shows, local variables x1 to x4 are allocated on the stack and have different sizes, expressing their locations as offsets relative to the stack pointer. The occupied bytes 24 to 31, 20 to 23, 18 to 19, and 17. Pointers to these locations are generated by LEA-Q instructions. Argument 7 with the value 4 and 8, a pointer to location of x4, are stored on the stack at offsets 0 and 8 relative to the stack pointer. When the procedure is called, the program will begin executing the code shown in figure 329B. Wait, what? I didn't follow that. Oh, it's this procedure over here. Okay. As shown in figure 330, arguments 7 and 8 are now at offsets 8 and 16 relative to the stack pointer because the return address was pushed onto the stack. When the program returns to call proc, the code retrieves the values of the 4 local variables and performs the final computations. It finishes by incrementing a stack pointer by 32 to deallocate the stack frame. Alright, local storage and registers. This set of programs, this is going to be the callee versus caller saved registers. So we'll have a practice problem on that, and then recursive procedures. We just have one practice problem on that. Okay. The set of program registers acts as a single source shared by all of the procedures. Single resource shared by all the procedures. Although only one procedure can be active at a given time, we must make sure that when one procedure, the caller, calls another, the callee does not overwrite some register value that the caller planned to use later. For this reason, x8664 adopts a uniform set of conventions for register usage that must be respected by all procedures, including those in program libraries. By convention, registers RBX, RBP, and R12 to R15 are classified as callee saved registers. When procedure P calls procedure Q, Q must preserve the values of these registers, ensuring that they have the same values when Q returns to P. Let me reread that. By convention, registers RBX, RBP, and R12 to R15 are classified as callee saved register. When procedure P calls procedure Q, Q must preserve the values of these registers, ensuring that they have the same values when Q returns to P as they did when Q was called. Procedure Q can preserve a register value by either not changing it at all or by pushing the original value on the stack, altering it, and then popping the old value from the stack before returning. The pushing of register values has the effect of creating the portion of the stack frame labeled saved registers in figure 325. Let's go back to that real quick to refresh. 325 save registers. So they go immediately after the address. Okay. So save registers come first, and then your local variables that you use, and then your arguments, and then the return address that you push onto the stack when you make your call. So there's really like 4 sections. Let me draw a little diagram, because I'm going to save this. Save to disk. This one would be called what? How do I? Oh, here. Blast. We'll just call this thing 2. And then we'll, oops. I hate it when the freaking mouse doesn't do what I want. Okay, 2, just to save it off. Please save. Can you save, please? There we go. And then we'll go up here and we'll say reset the canvas, confirm. And then we go in here and we want to do a call stack. So this will be a frame. The previous caller's return address. So here you're going to have your saved registers. And that's going to be followed by local variables. That's going to be followed by args 7+, and that's going to be followed by return adder. So that would be a frame, and then you would have multiples of these. So what's notable about this is that when you are in this frame, in this function, to reference arguments that are passed to you that aren't in registers, you have to index into, like pass the return address into the frame above. And if I go back to the diagram here, saved registers, local variables, arguments, and then the return adder. And I won't copy it because what the hell? Okay. I'll just save this, save to disk, and we'll call this, I hate this thing, okay, stack frame layout, AMD 64. Okay, cool. I just wanted to draw that to get it into my head a little bit more. Okay, let's continue reading. Okay, let's continue on the second paragraph. By convention, registers RBP RBX and R12 to R15 are classified as callee saved registers. When procedure P calls procedure Q, Q must preserve the values of these registers, ensuring that they have the same values when Q returns to P as they did when Q was called. Procedure Q can preserve registers by not changing it at all or by pushing the original value on the stack, altering it, and then popping the old value from the stack before returning. The pushing of register values has the effect of creating the portion of the stack frame labeled save registers in figure 325. With this convention, the code for P can safely store a value in a callee saved register. After saving the previous value on the stack, of course, call Q and then use the value in the register without risk of it having been corrupted. All other registers except for the stack pointer are classified as caller saved registers. This means that they can't be modified by any function. The name caller saved can be understood in the context of a procedure P having some local data in such a register and calling procedure Q. Since Q is free to alter this register, it is incumbent upon P, the caller, to first save the data before it makes the call. As an example, consider the function P shown in figure 334a. Okay. It calls Q twice. During the first call, it must retain the value of X for use later. Similarly, during the second call, it must retain the value computed for QY. In figure 334b, this is 34a, it has X and Y, passes Y into Q to U, passes X into Q for V, then returns UV. We can see that the code generated by GC uses two callee saved registers, RBP to hold X and RBX to hold the computed value of QY. At the beginning of the function, it saves the values of these two registers on the stack. It copies arguments X to RBP before the first call to Q. It copies the result of this call to RBX before the second call to Q. At the end of the function, it restores the values of these two callee saved registers by popping them off the stack. Note how they are popped in the reverse order from how they were pushed to account for last in first out discipline of the stack. So the first thing that we do, because these are callee saved registers that we're using, we push them RBP and RBX onto the stack so that we can use them. And then we decrement our stack pointer another 8 bytes for alignment. And then we copy in RDI and RSI into RBP and RDI. Save X and then use Y into the first call to Q. And then we save the RAX into RBX. So now we have RBP and RBX with X and U. And then we put RBP, which is X, into RDI. We call Q. Then remove then we just add RAX with RBX and store it in RAX. And then we add 8 to the stack pointer to deallocate the part that we aligned. I thought push Q would augment the stack pointer, so I don't know why it needs to be 16 byte aligned. Oh, it has to be a 32-bit align. No, it's already 8. So we got push Q 8, RBX 8, and then we add another 8 on top of that. I don't understand why you need 3 8s there. deallocate last part of stack, and then we pop RBX and RPP in reverse order. These are callee save registers. So this code demonstrating the use of callee save register. Value X must be preserved during the first call, and value QY must be preserved during the second call. Okay. Practice problem 3.4. Do I have any jobs here? Yeah. 3.34. Okay. Consider a function P which generates local values named A0 through A8. That's 9 local values. Okay. If they call this function Q using these generated values as arguments, shit, that's a lot of arguments. GCC produces the following code for the first part of P. So we push Q all of the callee save stuff, which is BP, BX, 12 through 15. We just push them all on the stack. And then we do our sub Q24. Interesting. Okay. Don't know what the extra 24 is for. So we got 8, 16, 32, 40, 48, 58, 68, 72. I don't know. I don't get why they do the sub Q there. Alright, then we move quad word RDI into RBX because we need to store off all of these things. RDI is a pointer? Oh, RDI is a value. And then we're just adding 1, 2, 3, 4, 5, 6. So there's 7 different one, 2, 3, 4, 5, 6, 7. And then RAX goes into this wherever the stack pointers. What? Oh, because RAX is being saved into the stack. Okay, so this sub Q here is for locals. So we save the return value. Don't know why we need to do, maybe because RAX is callee saved. And then RDI plus 7 goes into RDX. RDX goes into 8 plus RSP. Okay. Then we move 0 into EAX and we call Q. Okay. Some weirdness there. All right, 3 parts here, A, B, and C. A, B, and C. Identify which local values get stored in callee saved registers. Okay, well, do I have a table of what registers are callee versus caller? I don't recall seeing that. It was in his slides. I remember seeing that last night when I watched the lecture. But I do not see it in the book here. So I have to say AI. What registers on AMD 64? What registers are callee versus caller saved? My brain is melting here. Alright, so we got general purpose, okay. Callee saved registers. These are callee saved registers here. The two B's, the stack pointer, but I mean that's just like the normal stack pointer. And then 12, 13, 14, 15. Okay. So that would be let's move RDI into RBX. Wait a minute. Shouldn't have saved RBX before it moved it. That seems weird. Oh, but we pushed them all here. 1, 2, 3, 4, 5, 6. Okay, so we pushed them all. So BX 15, 14, 13, 12. BP. RAX is then used with RDX for the remainder. So these are going to be A0. So it'd be 0, 1, 2, 3, 4, 5. Yeah. So A would be A0 through A5. Identify which local values get stored on the stack. Well, there's 24 bytes of stack space allocated. And we move RAX into... Is RAX's caller saved? RX is just a return, right? So why are we even looking at... Oh, because we use here. Add 6. So A6 is RAX. Six. And then RAX goes into this stack pointer. And then 7. Then that gets stored into the stack pointer plus 8. So 6 and 7, A6 and A7. A6, A7. Because this says it's A0 to A8. There is no A8. Explain why the program could not store all the local values in callee saved registers. There weren't enough. All right, let's check our answers. This was 3.34. This example demonstrates the use of callee saved registers as well as a stack for holding local data. We see that lines 19 through 14 sorry, 9 to 14. Yeah. Save local values A0 to A5 to call save registers. So I got that right. Local values A6 and A7 are stored on the stack at offsets 0 and 8 relative to the stack pointer. After storing 6 of the local variables, the program used up the supply of call save registers to store the remaining 2 local values on the stack. That's pretty easy, now that I think about it. Okay, recursive procedures. The conventions we have described for using the register and the stack allow x86-64 procedures to call themselves recursively. Each procedure call has its own private space on the stack, and so the local variables for manipulating outstanding calls do not interfere with one another. Furthermore, the stack discipline naturally provides the proper policy for allocating local storage when the procedure is called and deallocating it before returning. Figure 335 shows both the C code and the general assembly code for a recursive factorial function. We can see that the assembly code uses register RBX to hold a parameter n after first saving the existing value on the stack and later restoring the value before returning line 11. Due to the stack discipline and the register saving conventions, we can be assured that when the recursive call to rfact n-1 returns line 9, that 1, the result of the call will be held in register RAX, and 2, the value of the argument n will be held in register RBX. Multiplying these two values then computes a desired result. Okay. So this is code for recursive factorial program. Standard procedure handling mechanisms suffice for implementing recursive functions. So we got rfact long n. Almost over the... Hey, almost finished. Pretty sure I can finish before 2. Okay, so we got r factorial, we pass in n, and there's a accumulator variable called result, where if n is less than or equal to 1, we just assign 1 to result and return it. Otherwise, and we don't need to have space for this result, we can just use EAX or RAX. It's a long, so we would use RAX. And then we have n times r factorial n-1. Okay. Says the compilation of it, we say rfact, we push quad word rbx to save rbx off because it's callee saved. We then move quad word rdi into rbx. So we store n in the callee saved register. Because we'll set it to something else when we call that thing. And then we move 1 into EAX, set the return value to 1, optimistically going down this path. And then we compare 1 with RDI. We could also do it with RBX at this point. And we jump if it's less than or equal. Go to done. I don't know why they do less than or equal. I guess that's for negative. Oh yeah, because n, the actual comparison, is less than or equal. Okay. Then we just return 1, which will pop RBX off the stack, store it in RBX, and do a return. Okay. Otherwise, we subtract 1 from RDI and store it in RDI. And we call r factorial. Since RDI is the argument, the first argument, it'll be nice and ready for rfact. Rfact's it, you're going to set REX. We then can use RBX, which we saved earlier, to multiply against RAX. and store it in rex so that it gets returned. Yep, that all makes sense. We can see from this example that calling a function recursively proceeds just like any other function call. Our stack discipline provides a mechanism where each invocation of a function has its own private storage. For state information, each invocation of a function has its own save values of the return location and callee saved registers. If need be, it can also provide storage for local variables. The stack discipline of allocation and deallocation naturally matches the call return ordering of functions. This method of implementing function calls and returns even works for more complex patterns, including mutual recursion, e.g. when procedure P calls Q, which then turns calls P. For a C function having the general structure so-and-so, GCC generates the following assembly code. What value does rfun store in the callee saved register rbx? A and B, and then fill in the missing expression in the C code shown above. All right, 7 minutes to do this. Let's go ahead and copy the C code. And I'll do it down here because that's going to be the solution to that. And I'll kill that because I don't need it. This is going to have an underscore for now. And this will have an underscore. And then this will be tabbed in a little bit. And so I'm on an X underscore. Long RV return underscore. Okay. ASM rfun I think I need to go down here. Oops. Copy that. Paste it in here. This is going to have a new line there. And then I have to do column selection here. There we go. And then I can just paste it right there. Okay. And then this obviously can... Let's do a search for percent S slot? No. Okay. Percent S search for white space, I think is S plus new line. No? R? I can't figure it out. Good enough. Okay. So this will be save off RBX. This will be put first arg into RBX. This will be put 0 into return. This will be a test first arg if it is 0, go to L2. This will be shift non-arithmetic right quad word. It's because we have an unsigned, and we're shifting right by 2. So divide by 4 RDI, divide first arg by 4, call R fun, add result to original arg first arg value, and then this will just be restore rbx ret. Okay, so we're getting this x, which is unsigned long. Makes sense. This will be a 0 because it's moving that into EAX. Then we do a test with RDI. RDI, of course, is the first arg. So we say if x, and because it's unsigned, we can just say if x. We don't have to compare it against anything. And then this is going to be a shift arithmetic right. I'll do the shift right. So this will be nx is equal to RDI, which is x, shift right by 2. And that calls at, stores that into RV, which is RAX. And then we add the original n, sorry, the original x with RV to get our new RAX. Okay, I think that's it. So that's so what does rfun store in the callee save register rbx? It stores, so if you look at rbx here, the first arg x, and then b is all this. Cool. And then we delete all this, and then we delete this, and then check our answer, and it's 2 o'clock already. Okay. So 3:35. This problem provides a chance to examine code for a recursive function. An important lesson to learn is that recursive code is the exact same structure as the other functions we have seen. Stack and register saving discipline suffice to make a recursive function operate correctly. Register rbx holds the value of parameter x so that it can be used to compute the result expression. The assembly code was generated in the following code. So x, I think if you say x equals 0 is the same thing as just saying x. Return 0. Actually, no. This would be if not x. I think that's equivalent. I think I have my, so this is equal, so it's saying, is it equal to 0? And then I think this is how you get, if x is positive, yeah, exactly, we got to invert that. Okay. And down here we have x right shift, yep, and x, RV, x plus RV, yep. Cool. All right, that is it. We are on the next section for array allocation and access, which I will resume. Actually, no, so I'm going to take a break for lunch here, and then I'm going to hop back on as soon as I'm done with lunch to, actually I gotta do cardio too. So I'm gonna eat lunch, do cardio, and then I'm gonna hop back on to watch a couple lectures. So here, we'll just say Vim readme. We'll go over here, we'll say, hey, procedures is done. Oops. There we go. Okay. I'm gonna go eat lunch, do my cardio. I'll be back on afterwards to watch some lectures. And maybe if I have motivation, we can work on the bomb lab as well. Cool. All right. I'll be back in a little bit then. Probably about an hour and a half.